Greetings and welcome back to Old Ways Rising Farm, where we have a project-related, specifically blacksmithing-related video for you today. I want to take a series of a few videos and discuss metal selection for your projects. This is a topic that can be very overwhelming for new smiths. There are so many different designations for different metals. There are so many different alloys and steels and irons and things out there, and in some cases the terminology about them is used in confusing ways or just plain wrong ways. You know, for example, a lot of cast iron goods are called wrought iron, which they are not. Pattern welded steel is often called Damascus steel, which it is not. You know, those are kind of the two most glaring examples. But there is so much out there, so much conflicting information. And if you go to any of the beginner blacksmithing, I don't want to call things out too specifically, but there are a number of social media platforms with beginner blacksmithing type forums that are filled with a bunch of knuckleheads that think they know what they're talking about and really, really don't. But will argue very, very passionately for their very, very wrong information. At one point, I tried to engage with some of these, and I just yeeted myself out of there as fast as I could. I just don't have the bandwidth for that craziness. So, I'll tell you a little bit about myself and how I came to blacksmithing. I started this craft about 12 years ago. And I started studying with a neighbor of mine who himself had studied with the Williamsburg gunsmiths. And I would go over to his shop, and he was making some historic reproduction black powder rifle barrels. He was making them out of actual wrought iron. We'll talk about that in a minute. Salvaged from old buggy wheels. And he needed a striker. So I would go over and I'd spend a couple days striking for him and helping him with his projects. You know, he'd work the mandrel and command things, and I'd strike with the two-handed sledge. And then he would help me with a project that I was interested in. So we would trade back and forth. And that's how I learned. And that is still, in my opinion, the most effective way to learn a physical skill is at the knee of an elder. It just really is, right? And so I was able to do that with him for about 2 or 3 years, and then he ended up moving. And I have since developed my own setup and been gifted quite a few things and have been very blessed in that way. So I have about 12 years, give or take a year, I don't remember exactly, of experience. There are many smiths who are far more experienced than I, because I have never done this full-time professionally. This has always been a hobby. And there have been periods where I was running around a grad school where I had no time for it, and periods where I've had a lot of time for it. So it's being a little bit off again, on again in there. So while I do have quite a bit of experience, certainly enough to talk to you about these basic topics, there are some people out there that have a lot more experience than me. And if we are in conflict, you should believe them, right? So a couple of other YouTube channels you should check out if you haven't found them already. If you're watching this video, you should go find Black Bear Forge. You should go find Purgatory Ironworks. You should go find Christ-Centered Ironworks. And you should go find Rowan Tyler. Okay? His channel isn't uploading anymore. He got busy and kind of went away from YouTube. But his content that's already there is some of my favorite blacksmithing content out in YouTube. So I would recommend those 4 to you. And if something I say is in conflict with either of those 4, believe them. They have more experience than I do. Okay? But I do hope that this video will be useful to you, especially for beginners, at cutting through some of the static and helping you to organize your thoughts and approach this topic a little bit more productively. Now, the first topic in choosing materials is going to be recycled or not recycled. And this is going to bring a lot of controversy to bear very, very quickly. And you're going to find two very extreme camps out there. Some that only want to deal with recycled metal, and some that don't even want to touch it, like it's cursed. Okay? I'm in the middle, so I'm probably going to anger both of those groups. Okay? But there are some pros and cons to recycling steel yourself. And there are some cases where you want to, and some cases where you should not. The second and the third video in this little series are going to be specifically about recycled steel. Most of what I work with is recycled steel. Okay. Now, I'll give you the con first. The people who don't want to hear about recycled steel ever under any circumstances are almost always knife makers. Okay? Now, if you think about the physics of a knife, you have a very thin wafer of steel, which is very, very hard. When you're choosing steels, there is always a trade-off between hardness and brittleness. Okay? As it gets harder, it gets more abrasion resistant, but also more vulnerable to shock, cracking, and breakage. As you get softer, you get less vulnerable to shock, cracking, and breaking, but you lose abrasion resistance. Okay? A soft steel will take the same degree of sharpness as hard steel, because all sharpness really has to do with is the angle of the cutting edge. So a finer angle is sharper, a more obtuse angle is duller. Okay? And as cutting edges evolve and dull, you're kind of making the tip more and more obtuse with time. Abrasion resistance slows that process. So mild steel can take the same angle as the best hardened steel, but as soon as you try to cut a marshmallow, it's going to roll over and lose all of its sharpness. Right? Hyperbole, but you know what I mean. So when you're talking about edge-holding steels, you're pushing it to the extreme of hardness so that you can retain that sharp edge. Okay? That's the goal. Now, you want to retain some degree of toughness as well, otherwise it's just as fragile. If you take like a super hard super steel, like 52-100 or something like that, and you cut it down to a 10-degree bevel, and you harden it at a high temperature and don't anneal it, you're going to have something which is absolutely crazy screaming hard. But it will dull as fast as mild steel, because that edge is just going to snap right off. Right? So you're looking for a balance of hardness and toughness, and the sweet spot for knives leaves a lot of brittleness in place. You ameliorate some of the brittleness with the tempering process, but it's still a relatively brittle wafer. Therefore, it has to be flawless. And this is where knife makers get a bitter hatred of recycled steel, because recycled steel, even just from pit rust, is going to develop weak spots, have work-hardened spots in it, have pre-existing cracks in it. It's guaranteed to happen. Even, like I said, something which has been babied its whole life but developed some pit rusting, the bottoms of those pits is a stress point that will develop a microfracture in the forging process. Okay? Now, you can take it off with a file. It's not a deep blemish, but if you just have deep pit rusted steel and you go to whacking on it, you're going to develop cracks. Okay? You need to grind those off first if you're going to use that material. Or throw away that section, which is my approach. So professional knife makers cannot tolerate that risk. They need to be able to make a blade. They need to be able to make it quickly as possible, because they're going to be billing their shop hours at $50 to $100 to $200 an hour. So if you take the low end of that and you assume it takes 3 or 4 hours to forge a blade, if that breaks, you're talking about $3 or $4 worth of high-end new steel versus 10 cents worth of recycled steel. But you have several $100s worth of fuel and billable shop time invested in the piece. So saving $3 does not justify losing $300. Okay? So shops that are thinking that way, those are the ones that loathe recycled steel. If you're not making knives or edge tools, you can get away with a lot more because you're going to leave it soft. So yes, the material is still going to have flaws, but those flaws are not going to be nearly as big a problem in your end product. If you're baking a tent stake, just use what you have and don't overthink it. Okay? Because you're not going to harden it and you're not going to break it because it's in thick cross-section. Okay? So when should you and when should you not use recycled steels? Well, if you're not experienced, you don't know how to recognize where some of those fracture points are, and you're making thin edge tools, you should never use a recycled steel. Okay? There's also certain recycled steels that you should never use for edge tools, and we'll talk about that. And some of them are popular that people do like to use for edge tools, but I would advise you avoid it. If you are a little more experienced and you're willing to throw away the junk spots, and you're a little bit better at recognizing how a piece was used in life and predicting where those hard spots and tough spots and broken spots are, and the way you gain that knowledge is by breaking a lot of blades prior to that. If you're willing to go through that learning curve, sacrifice a substantial amount of your work to learning curve, then you can go ahead and make edge tools out of recycled steel. You will still always have a small failure percentage even under the best of conditions. If you're willing to accept that, go forth. Do the thing. If you're going to make things in thick cross-section, now I'm leaning toward recycled steel. Save a little money. If you're making things in thick cross-section that are not hardened, now I'm going to lean heavily toward recycled steel. Right? If you're doing decorative ironwork, bookends, tent stakes, grapples for trapping, these are all some examples of projects that I've made out of recycled soft material, go for it. Don't even worry about what it is. As long as it's not cast iron, you'll be able to forge it, and it's going to be soft. You're fine. Okay? So before you think any further about your material selection, think about where you fall on that gradient. If you want to be a knife maker, buy new material. If you want to be a general blacksmith, you're going to buy new material sometimes and use recycled material sometimes. If you want to be a demonstrator at Black Powder Meets and all you're going to do is, tent stake and trap grapples, go full recycled. Okay? So there are arguments for and against all of those things. For the rest of this video, I'm going to dive into some of the details of different metallurgies, and what I'm going to say here will apply equally whether you decide to go for recycled or new material. Okay, so let's talk about some of the details and some of the terminology and untwist a little bit of this so you can better understand what blacksmiths are talking about when they're describing the materials they use. The first distinction I want to draw is cast iron versus steel. Okay? So as we add carbon to iron, we get a couple of things occur. The first, at low percentages of carbon, and you'll hear people talk about points of carbon. 1 point of carbon is 0.01%. Okay? So 100 point carbon is 1% carbon. Okay? This is worked into a lot of alloy names like 1095, 1080, 1090, 1095. Are those last two numbers, 80, 90, 95, are points of carbon. So it's 80 point carbon, 90 point carbon, 95 point carbon, right? So 0.8%, 0.9%, 0.95%. That's what we're talking about there. As you start adding carbon to the iron to make steel, I almost said that backwards, the carbon atoms interact with the iron atoms. At low concentrations, they restrict the mobility of the iron atoms. So raw electrolytically pure iron is a very soft, very ductile, spongy material. It's spongy because of the properties of metallic bonding. We're not going to get into all of that today. At some point here I will do a video specifically on heat treating where I will get into all of that. But it's spongy and ductile because the atoms have a certain degree of freedom of movement relative to each other. They can wiggle and jiggle and move without breaking the metallic bonding structure. As you start to stick carbon atoms in there, really any alloying element in there, it gives them something to bump into which restricts their motion. That makes it harder and increases the tensile strength at an ever increasing detriment to the plasticity and therefore the resilience of the material. If something is very plastic and squishy, you can pound on it all day. It's just going to squish around. It will never break. As you restrict that freedom of motion, you get less squishy mushiness, more solidity, more strength, more hardness, and more tensile strength. But it's easier to break. Okay? So as we walk our way up at low concentrations of iron in the steel, I did say it backwards that time. Any carbon in the iron makes it steel and makes it stronger than raw iron. Okay? So as we walk up toward 18 or 20 points of carbon, we get mild steel. It's just enough there to restrict the motion of the atoms and give it a bit of a bump in tensile strength, but not enough to start making it brittle. Okay? Then as we go up to 40 and 50 points of carbon, we get something that can be hardened, but something which is still going to be reluctant to hold an edge. When we get to 60 and 70 points of carbon, we get enough hardenability that it makes a really good impact edge, like an axe or a hatchet type tools. And then when we get 80, 90, 100, or some alloys like W1 even a little bit over 100 points of carbon, now you get really hard, very abrasion resistant, edge holding steels. Okay? But again, we're into brittle territory. Now, as we get, there is more to it, and there's a lot more to the heat treating process than this very, very quick cursory glance. But again, I want to keep this simple for this video. As we go over 100 points of carbon, something else starts to come up. And this is, the chemistry term is colligative properties of solution. And anytime you make a solution, no matter what you dissolve in what, there's a couple things that happen. Okay? One of those is that it lowers the melting point. This is why salt melts ice. You put salt on top of ice, it lowers the melting point of the water, and the ice melts. When you put carbon in iron, it lowers the melting point of the steel. But it doesn't become a dramatic effect until you're approaching 200 points of carbon. But at this point, you get a material which is much easier to melt and cast, which is why we use it for cast iron. But at this level of carbon, it is so profoundly brittle, it's no longer a forgeable material. That's why your forgeable steels tend to stop in the ballpark of 100 points of carbon. And your cast irons tend to start around 200 points of carbon. Okay? And they tend to hang right around 200 points of carbon because of the brittleness factor. You don't want to get too brittle that it's, your cast iron pan breaks like glass. You don't want to get in that territory. And you can get in that territory with enough carbon. Okay. So cast iron is high carbon material. So much carbon that you're really focusing on the melting point reduction and not the physical properties of the material anymore. Okay? Now, the next set of distinctions I want to talk about is age. Pre- and post-Bessemer process. The Bessemer process comes and was patented in 1856, and this is what really opens up the modern age of steel and steel-making materials. Okay. This is a process where the crude, unrefined iron would be melted in a gigantic crucible, air bubbled through it, and that burns off all of the impurities. Everything from Bessemer process on, I'm going to talk about in the next chalkboard. What I want to talk about on this chalkboard is the pre-Bessemer, the real antique materials. So this starts with charcoal iron. Pre-1780, everything that you're talking about is charcoal iron, made in small, and then later on, as we get into the 1700s, not so small, tall smelting furnaces. Okay? And the smelting furnace, again, I'm not going to get into the full chemistry of iron reduction and what's going on in the smelting furnace, but these small force-drafted furnaces, they would smelt the metal, but they would not get hot enough to melt the iron or the steel that comes out of them. So what you get is you have little globs of ore percolating down through. Where they touch each other, they weld into larger and larger clumps. And then the fuel underneath them burns out, and then they drop down further and weld to another bunch underneath. Right? So what you get out of them is a very, very porous material. As it is smelting, it has the opportunity to absorb any carbon it comes in contact with. So some globules that are far away from the air draft and are coming in contact with a lot of the unburnt fuel will absorb carbon way up into the cast iron range. Others will not absorb as much, and still others close to the air blast will have the carbon burnt out of them and they'll be fully decarburized. So you'll have everything from almost pure iron up to extremely brittle cast iron, and you just get like a sponge of this material. It is utterly useless in that original form. So it has to be exposed to enough air draft in a secondary process that it leaves cast iron territory and becomes forgeable. And then it has to be hammered out thin and welded back together, and hammered out thin, and then welded back together, and then hammered out thin, and then welded back together. That is that hammering process gives us the first form of what we now call wrought iron. Wrought simply means hammered. Okay? So the oldest form of wrought iron that actually is wrought iron is a hammered out bloom. The bloom being that spongy mass that comes out of one of these early furnaces. Okay? And then in the late 1700s, they developed the puddling process, where you would take iron blooms, put them in a furnace that was coal-fired. This is also kind of the transition from charcoal process to coal processing of the material. And it was partially remelted, mixed with a bunch of minerals and fluxes and scale that would react chemically with the impurities and the excess carbon, and much more efficiently burn it off. That would result in a very viscous lump that you could pick up with tongs called pig iron, which was then also had a lot of inclusions of slag from the puddling process itself, and it also had to be hammered out thin and forge welded back together a couple of times as a final refining process, giving us the later version of what we call wrought iron. Again, hammer purified iron, basically. Okay. Now, a lot of cast iron in modern day is termed wrought iron, and if you just Google wrought iron, and look for a wrought iron railing, in modern day we've forgotten this distinction, and wrought iron is often used as a synonym for decorative iron. Okay? But modern decorative iron is almost always cast iron and is not useful as a recycled steel. Okay? Now, once we get the Bessemer process, things started to switch over, but there were puddling furnaces in operation into the early 1900s. There are none currently in operation today. So if you are looking at wanting to do reproduction ironwork with authentic old materials, you have to recycle. This is another case that argues for recycling steel. I strongly recommend, if you're just thinking about getting into blacksmithing and you came to this video just to learn some basics, avoid this for now. Never miss an opportunity to buy it and put it in your stash, But don't try to work it until you have the opportunity to get some experience with regular materials and the opportunity to work under the tutelage of a smith that is experienced with it. If you work it at too low of a temperature, if you try to work it in a propane forge, if you try to work with it the way you would work with modern steels, you're only going to have frustration, you're going to shred it, and you're going to ruin a very valuable antique material. So leave it alone until you have a solid fuel forge and somebody to teach you how to use it. Okay? There are expert smiths who can work wrought iron successfully at a propane forge. But don't try it. Don't try this at home. Okay? It is extraordinarily difficult to get a propane forge hot enough to work in the range that wrought iron wants to be worked in. So stash it for later. Don't ruin it in one of your early projects. Just work with some mild steel and get the hang of it. Now, further processing of these materials, you get crucible steel and blister steel. So if you take your wrought iron and you forge it out really thin and then case harden that, and then, which is just heating it in contact with carbon so that carbon is absorbed by the steel wafers, you will get the majority of the thickness carburized, and then a couple of forge welding processes will homogenize that carbon content. That's blister steel. That's the really old school way to make steel for knives and springs and things like that. Very labor intensive. The other process is crucible steel, where you would take some of this wrought iron, measure it out with a predetermined quantity of carbon, put it in a crucible, and melt it so that that carbon is absorbed homogeneously through the material. The oldest crucible steel in the Western world was done in Damascus. They were using an ore which was high in vanadium, and that would allow for the formation of carbide crystals, which would leave a characteristic pattern in the finished steel. That's where we get the term Damascus steel. And in its day, it was the only crucible steel that was available to smiths in Europe. And it was recognizable because of the crystalline pattern. So people started to want to fake that crystalline pattern with forge welding processes, which gave us pattern welded steel. And now, because it was developed to fake Damascus, people have just subbed the term in. So this is where you get your confusing definitions of Damascus steel. That's the nutshell history. So crucible steel and blister steel are the old school ways of taking charcoal iron or puddled iron and turning it into a good edge holding steel. So everything from then on goes to Bessemer and later, where we get the named alloys we know and love today, and we'll talk about that in the next chalkboard. So we talked in the previous boards about the early types of iron and steel based materials that were available. But once we get into the Bessemer process, and that very quickly was replaced by open hearth furnaces and mass production of steels, we get into a large number and a proliferation of alloys. The interesting driver to a lot of this was the pre-dreadnought and dreadnought warship arms race of the late 1800s and early 1900s. That really pushed steel technology forward. And a lot of the material from these first round of production houses was sucked up by their relative navies. So there wasn't a whole lot of it in general tooling. So you still see, a lot of tools being made out of crucible steel, which was kind of a modern equivalent of the original Damascus in England, where they're taking the puddling process materials and bumping them up a notch, using modern furnaces, but still using the cheaper, more available materials, because this stuff was relatively rare. But as we roll into the interwar times, manufacturing just exploded across the world, and these sorts of materials became widely available, and that's what really replaces the wrought iron with the modern steels. Okay? So I want to talk about a few of these alloys. Some of these you've probably heard of, some of these you probably haven't heard of. But I want to talk a little bit about what putting something in iron does to the finished material to help you understand what you would want to pick. You go onto, blacksmithing forums and you'll see a lot of questions. Well, what kind of steel is best for the knife? And the answer is all of them, if you know how to use them properly, can be used to make a good knife. It's more which of them fits the combination of your skill, design parameters, and technical capabilities, facilities, right? Everything on this board, except for that one, can be used to make a knife if you do it right. Everything on this board can be used to make a tent stake if you do it right. And everything on this board can be used to make a hammer if you do it right. Okay? So there isn't so much a right or wrong answer to this as there is a big giant it depends. So you, as the craftsman, need to understand what these things mean so you can pick the right combination of materials for your skill level and facilities. Okay? And that's where we get into all of these arguments, because one person has the skill level for one thing and makes a great tool, then picks up something that sounds fancier, and they don't have the skill level to work with it and makes trash, and then you get all of these arguments over, well, this was good and this wasn't good. Well, no, this was properly used and the other wasn't properly used. This is a better way to understand it. So let's start with the basics. We've talked about iron and steel being carbon in iron. And these are our oldest classic steels, the 10 series. The first number indicates the series of alloys, and the 10 series alloys means nothing but carbon. So iron with some quantity of carbon. 1018 through about 1025, those are your building steels. This is your I-beams and steel girders and what the bridge you drive on is made out of. This is the mild steel that if you go to a welding shop and you ask for mild steel round stock to make some tent stakes, it's going to be 1018. Okay? When we move into 1075 and 1080, we get into spring steels. Your classic spring steels. Most coil steel is this stuff, right? This is what your crowbar is made out of. This is what your hammer is made out of, probably. This is what a lot of stuff is made out of that you want kind of that medium hardness. You can forge it, you can harden it with a quench, you can temper it to everything from really soft that you can bend it in a vise and, make tools that you can modify after the fact, all the way up through things that are hard enough to take a pretty reasonable edge and make a great hatchet, right? That's in here. 1090, 1095, those are good for your really sharp edge tools that you want to prioritize edge holding. So, this is not what you want to use for a hatchet. This is not what you want to use for an axe or a hacking knife or a froe or anything like that. This is what you want to use for your delicate carving tool, your chef's knife, things like that. Okay? But the 10 series can do literally every single task a hobbyist could ever want to do. Let me say that again. The 10 series can do literally every single task that a hobbyist could want to do. You do not need to go outside of the 10 series to accomplish any practical purpose. So if you're watching this as somebody who's very new to blacksmithing or somebody who hasn't smithed and wants to get into it, my advice to you for your beginning projects is to go purchase brand spanking new 10 series steels so you know what you're looking at, you know what you're working with, and as long as you pick the right one, low, medium, and high hardness, and then work on your heat treating skills, make sure you normalize. We'll talk about that in a heat treating video. Work on your heat treating skills. You can get any project accomplished just with the 10 series. Don't let yourself get distracted by all of the clutter of all of the other alloys out there. Okay? Stick to these. You don't need anything else on this board. Stick to these. Now, if you're an intermediate or advanced smith, well, if you're an advanced smith, you're probably not watching this video. But if you're an intermediate smith and you have some experience under your belt and you want to start exploring, let me talk to you about the rest of these alloys. Okay? Also, if you're an intermediate smith and you want to get into recycled steels, you're going to find a lot of these alloys in your recycled steel toolbox or pile. So, we want to know what these are, at least at a basic level to understand them. So, the next alloying element I want to talk about is nickel. Okay? It's still a steel, it still has carbon in it, and it's still an alloy because an alloy is any mixture of two or more metals. Right? So, nickel is used in steels to increase their ductility and help them be more resilient. Okay? Also, at very high quantities, 8-10% nickel, they contribute to rust resistance. So nickel is important in stainless steels. So the classic examples that you may run into as a hobby recycler are old saw blades. Now, small saw blades, like a homeowner circular saw type saw blade or a homeowner bandsaw, those are almost always 1080 through 1095, one of these guys. But when you get into big industrial saw blades, big sawmill saw blades, whether it's band or circular, usually they're made out of a high nickel steel because they have a lot of friction, a lot of temperature buildup, and they have to flex a lot without taking a permanent deformation. Okay? And the nickel helps them be a little bit more plastic so that they can withstand that flexing force and not crack. Okay? So it's really a specialty purpose. And L6 and 15N20 are the two dominant alloys used for those type of saw blades. They're both 2% nickel. L6 is about 70 points of carbon and 15N20 is about 75 points of carbon. So they're a medium carbon, low nickel steel. Or medium carbon, medium nickel steel, I'll say. Less than 1% would be low nickel and 8 or 10% is high nickel, right? So medium carbon, medium nickel. L6 and 15N20. That's where you'll bump into them. They're medium carbon, so they're not going to take as sharp an edge as your 1080. Okay? But they have a little bit more elasticity is the best word for it. Chromium. The primary reason that we add chromium to steels is to modify the heat treatment requirements. So when you add chromium to steel and then you harden it, the hardness penetrates deeper into the steel. Okay? So these steels, the 10 series, usually if you have a thick part and you harden it, it's only going to get surface hardness. The hardness won't penetrate the entire core of the piece. Okay? Now, if you have a thin knife blade, it's nothing but surface. But if you have a whole homogeneous axe head, and the whole axe head is 1095 or 1080, well, you wouldn't want 1095, 1075, and then you harden it, the outer 1/8 inch or maybe even 1/4 inch will harden, but the core of that will remain a little bit soft. Now, that can be an advantage, but it does mean that as you're sharpening your axe head, eventually you will sharpen all the way through the hardened component. Okay? Though it does contribute to resiliency, so that may or may not be something that you want. When we grow to the chromium-containing steels, the low and medium carbon chromium-containing steels, they will harden. They won't get as hard as your upper 10 series, but they will, what hardness they develop, they will take through the entire core of the piece. Okay? So this is where we get our engineering steels. Your medium carbon, low chromium engineering series, your 4140, 6150. These are your axles, your car axles, your truck axles, your hydraulic rams. Drill rod is sometimes this. Like a water well drilling rod is sometimes this stuff. Sometimes like masts for antennas and like big antenna installations will sometimes be this stuff. The engineering steels, where you're not trying to make a real hard material, but you're trying to make a real consistent, extremely rigid, resilient material. That's where the chromium comes in. 5160 is a common spring steel. It's a compromise between your classic engineering steels and your old-fashioned 1080, 1090 spring steels. It's a compromise between those two. And then air hardening steel, like A2, is up to 5% chromium. And when you get that much chromium, just heating your piece red hot and setting it on your anvil and walking away is enough to quench it because of the impact of that chromium. Okay, so that's where you get your air hardening steels from. And it's also been used in some of the first generation high-speed steels, like D2 is 12% chromium. Okay? Beginning smiths, I would avoid A2 and D2. They have very specific heat treating requirements. You don't want to mess with those unless you have a temperature control oven. And, 41, 51, and 61 series steels are good, but I would think about those as more like an impact tool class. As a beginning smith, you're going to want to use them definitely in oil quench. Never touch them with water. You can get away with water on these if you know what you're doing. You still should use oil quench at like the 80 and up. But these engineering steels are good for impact tools like a hammer. If you want a tool that you don't want to crack, that you're going to be thumping around a lot, but you want a little bit of hardness in it, use one of these 41, 51, or 61 series steels and don't quench it. Okay? Because these alloying elements are going to harden it a lot without needing the quench, and you're not going for edge retention anyway. You're going for impact resistance. So if you want to make a hammer as a beginning smith, I would use something like 5160 or 4140 and then don't quench it. And you'll have a pretty good result there. Okay, just leave it as forged soft. Now, silicon, you'll bump into this in one specific region, and that's your S-series steels. This is shock-resistant steels. So silicon is close in the periodic table to carbon. It has some of the same behavior when you add it to iron as carbon does. But you can get a high hardness without as much brittleness by adding silicon to the alloy instead of adding only carbon to the alloy. So S5 and S7, this is what your jackhammer bits are. Okay. I like to use those for anvil tools. That's about all I use them for. They are oil quench steels, like most of the rest of this. And then the last category I'm just putting in is a group, the refractory metals. So this is the kind of the left-hand half of the D block elements if you're looking at the periodic table. But the ones we're really talking here are tungsten, vanadium, molybdenum, titanium. Those metals. Okay? And what these are usually used for is modifying the high temperature properties of your alloy. Okay? So your classic high-speed steels, like drill bit steels, drill bits produce a lot of heat, especially if you're drilling through metals, a lot more than a saw blade with your L6 and 15 and 20 are going to need to tolerate. So they need to be sharp enough to drill steel while they are, 500, 600, 1,000 degrees from the friction. So adding these refractory metals helps them retain their hardness at those high temperatures. They are not forgeable. Do not try to forge them, especially as a beginner. 52100 is bearing steel. It needs some of those same characteristics. It is forgeable, but again, you're not going to get enough out of it without a heat treating oven to make a tool made from this better than a tool made from these. Especially if you're a beginner, right? You really need to see the difference between a 52100 part and a 1095 part. You need either 15 or 20 years of experience, and then it's still dicey, or a heat treating oven, right? If you have a heat treating oven, you can make some amazing things out of this steel, right? Now, if you have the chance to get some big bearings, get them, put them on your stash, just like I said with wrought iron. Put them on your stash for later, right? But don't worry about this early on. And H13 is a really interesting one. It's got quite a bit of chromium and low levels of these refractory metals. And it's a good high temperature tool steel. So it was developed for dies for stamping metals that are still glowing hot coming out of a steelworks. Okay? So this was developed for high temperature stamping dies. Like in big drop hammers. Like factories that are like making tank armor and things like that. That's what this was for. It is a forgeable steel. It is air hardening, like your Air 2. Do not try to quench it. And it is very good for making anvil tools. It's also very hard to find, and you'll never see it as a recycled material. So this is just kind of an overview of how to think about some of these things. Again, I want to reiterate, as somebody new to the craft, stick to the 10 series. And then when you want to branch out, look at some of these engineering steels. Okay? When you start wanting to make your own forging hammer, when you start wanting to make some things like that, then you can look at some recycled steels from like car axles and things like that, and have some really good material in here that can be oil quenched carefully with a lot of practice after you've gotten some experience under your belt, or just left soft for like a soft face hammer for striking other steel tools. This is really good for that sort of stuff. So leave the rest of this chart for 2, 3, 5 years from now, when you've had a lot of experience with this and some experience with that. Then you can branch out into some of the other stuff. Thank you so much for joining us with this video. If you've enjoyed it, I hope that you'll give it a good old thumbs up so the YouTube algorithm knows to show it to other folks. I hope that you have found this very, very ever so brief, oversimplified explanation of metallurgy useful and helps declutter some of the terms and arguments that are going on out there in the social media blacksmithing space. And if you have, I hope that you will subscribe to the channel, because the next video that's coming, I'm going to go out into my stash of stuff and pick out some examples of recycled and recyclable materials, talk about what they're made of, and what sort of projects I would choose for them. So I hope that you will have a wonderful, blessed day, and join us here next time at Old Ways Rising Farm.